All right, so for now, we're going to define continuous as really anything that doesn't contain a gap or a hole or an asymptote, right? So it's kind of weird because I'm going to say that a continuous graph is a graph that does not contain a discontinuity, which uses the term in its own definition, but there's a limit-based definition for continuity. And so we really can't talk about that just yet without getting into limits. So once we talk about limits, we'll circle back and talk about continuity again, right? But for now, does not contain a break in the graph. All right, so it doesn't contain a break in the graph. All right, very simplistic definition at this point, but like I said, we'll circle back on that. All right. Yeah, so that was like in any kind of asymptote, a hole, or anything like that, which would constitute a break. And I'm actually going to detail the different possibilities at this point. Um, there is an exception because you could have what's known as an oscillating discontinuity, and it won't appear at first glance as if there's a break, but there is a infinite component to it. Right? So
Infinitely oscillates but never approaches zero.
yeah, so what'll end up happening is it'll seem like it's almost a smooth curve, but the more you zoom in, the more you see the oscillation, and the more you see the oscillation, the more oscillation there is. You keep zooming in more and more, and you keep seeing more and more. All right, so we'll get to that. It's on the next page if you want to look ahead, but we'll start off with a point discontinuity, also known as a hole in the graph. All right. If there's a common factor top and bottom, then most likely you're dealing with a point discontinuity. All right. So look for a common factor top and bottom. All right. So that would normally require us to factor the top and bottom, but there is kind of a workaround. If you're dealing with polynomials, a polynomial division, you don't necessarily have to factor. You can use other techniques like long division or synthetic division, right? But in this case, it's not terrible to factor, right? I have become aware over the years that people tend to forget things like how do I factor a difference of perfect cubes. So I'll just give you the rule here real quick, and then I'll show you multiple approaches for simplifying this. All right. So if you have a cubed minus b cubed, by rule we're going to say that that's equal to a minus b, a squared plus ab plus b squared. All right. So the top here. So you're going to take, in order to find the binomial factor, you're really just taking the cube root of each part of the difference of perfect cubes. So it's going to be x minus 2. And based on the fact that this is related to a point discontinuity, we know that the example that I choose must have a common factor, otherwise it would not demonstrate a point discontinuity. And so if it is going to factor and in fact have a common factor, then one of the factors at the top has to be x minus 2, otherwise there would be no cancellation. Right? But the rest of it is, you look at the cube root of each part of the difference of perfect cubes, and then square whatever the a value is. So that's going to be x squared, x squared. All right. Then multiply the a and b values. So a and b. I keep doing that. X and 2, so 2x. And then square that last value to give you 4. And just get your signs in there.
Just to be clear,
Mm-hmm.
the b value is the denominator b.
The b value.
So when you're like multiplying the a and the b,
No, just factor in the numerator.
Yeah, I haven't even touched the denominator yet. So when I,
There's a cube, because 8 is also a perfect cube. 8 to,
Oh,
8 is just 2
oh
to the
my
power
God.
of
Right.
3, so you got a cube.
Sorry,
there.
I was completely doing a different thing. No,
All
that
good.
makes sense.
so then on the bottom, we have our x minus 2. So that's my f of x function in factored form. But I do have that common factor that could cancel out. The thing is, the original form of the function and the function after you've canceled the common factor, they're not directly equivalent to one another, right? Because it's kind of like when you were solving a quadratic, or actually any kind of equation. If you divided both sides by a variable and it canceled out, that meant that you were losing a solution in most cases. All right. So you think about the different things that you can do when you're finding a function or working with a function. You could find x-intercepts, you could find y-intercepts, you could find points of discontinuity, you could determine end behavior, you could determine whether it's increasing or decreasing. Right. So any factor that involves a variable could impact any of those things.
I would just have done like derivative of the, like just use quotient law.
Right, and I'm going to caution you because that's going to get you in trouble in the first unit. All right, because when we're doing things analytically as it applies to limits,
Yeah.
we're kind of pretending we've never heard of the term derivative. Right, so any derivative shortcuts, like, I mean, you might consider, I'll just use L'Hopital's rule or something like that. It's like, that's great, but the skills that we're learning now are going to be related to everything pre-derivative.
I wouldn't have even factored in just like x, 3x squared.
All right, so we have that common factor. I'm going to pull that out and set it equal to 0. All right, and so we're going to get x equals 2 there. All right, so that is the x value of the whole. All right, so that's the x value of the whole. Now by simplifying the function, all right, so you go ahead and cancel now, we would get, I'll just say y equals x squared plus 2x plus 4. If I want to find the y value that corresponds with the whole, I wouldn't plug the 2 into the original function because that's just going to zero out. It gives you what's called an indeterminate expression. All right, you get 0 over 0, which is not equivalent to 0. It's not undefined. It's something called indeterminate that has a special place in the whole hierarchy here. So what I would do is take my simplified form and pop in the 2. So y of 2, 2 squared, 2 times 2, plus 4 is going to give me, was that a 12? So the whole is at 212. My pen is acting up now.
When you say whole, do you mean like vertex or
I, yeah, open circle, like a literal hole in the graph, which I'm going to plot now so you'll see it.
okay?
All right.
I just never heard of it before.
Just fix this. All right, so yeah, 212. But let me pull up the calculator and show you some things there. So we played around with this a little bit last time. You can see I haven't touched it since. So we're going to have x squared. Well, you know what? Let me put the original function in. Getting my calculators confused here. Alpha, y equals to bring in the fraction. X cubed minus 8 over x minus 2. Lock it in, hit OK. Okay, wrong calculator again. Hit enter. All right, so you can go into the table. If the hole is at a clean number, the x value for the hole is clean, it'll show up in the table and you'll see an error. All right. So go into the table, second graph, you see an error at 2. All right. Now, if you follow the progression here, maybe you can kind of figure out that it's 12. But what I'm going to do is I'm going to go to the graph, zoom 6. All right. Now, here's the x value of 2. 12 is off the grid because this is a negative 10 to 10 window.
I would just do go to like window.
That's
Yeah.
so in window, I'm going to go to Y max. I'm just going to make it something bigger than 10, something reasonably bigger. Now, the fact that we already know that it's 12, I can kind of tailor that into the conversation or throw it in. Also, let's say we didn't know that. In the table, I know that at 1 I'm at a height of 7, at 3 I'm at a height of 19, so 2 is going to be a height somewhere in between 7 and 19. So I'm gonna choose something in that neighborhood. I can go as high as 20 if I want. It really doesn't matter. 15 is going to do the job. So I'm going to hit graph. For those of you who are not 100% familiar with these calculators, once you edit the window, just hit graph to bring up the display. If you then do a zoom 6, you're going to undo all your changes. All right, it happens all the time. That's why I'm bringing it up. But I know that there's a discontinuity. Looking at the table again, at 2, there's some form of error on the graph, but it's not visible in the picture. Right? It's not visible because it's not a vertical asymptote. Right? It's not visible because the calculator doesn't have, unless there's something in a new update, it doesn't have the ability to really just point out the location of the hole. So I can trace along if I want and see if I can pick it up that way. You know, sometimes you could, like if it were a multiple choice question on a test, I'm at 1.96 and it has a height of 11.8. I'm at 2.12, it has a height of 12.7. So somewhere in between the 12.7 and the 11.8 is going to be my answer, and I would look for the choice that it falls in that interval, right?
What's like the reason why that happens, like in the graph?
What's the reason why a hole happens in the graph? Because there's a discontinuity, but the limit, and we're getting ahead of ourselves here, the limit coming in from the left and from the right are all approaching the same y value.
Okay.
Now, in the case of an infinite discontinuity, as you approach a particular x value, the limit will go to infinity or negative infinity, so you know there's an asymptote there. All right? So you can kind of pick it up that way. Another way you could do it, I suppose, but it is all reliant on it being a set of clean values, is I can do a second trace value, plug in the 2, hit enter, and it'll bring me to the location of the hole, although there's no blinking cursor like in the old model, so it just tells you that there's nothing going on there, which kind of sucks. The older calculators used to blink at that location, so I don't know. All right, so maybe that's not as viable of an option. But I just kind of look at it like you have a discontinuity. It's clearly not an asymptote according to the graph. So by default, or we will default to that being the location of a point discontinuity. All right. So in terms of the parabola itself, you graph your parabola by ordinary parabola graphing techniques, whatever you're most comfortable with. So if you could find symmetry in the table, that's great. Not always going to be the case, but if you could find it, that's good, and we have that here. Right, so my vertex is at -1, 3. Let me just bring this over here. So -1, 3. Oh, but I have to go up as high as 12. So I'm going to go by 3s. All right, so -1, 3. In terms of the width, I'm fine. -3, 7. Let me get that in there. That's going to be in this neighborhood. -2 is 4, somewhere over here. 0, so we have symmetry. We can just follow the trend. And then at 2, we have an open circle. And that's generally what your graph is going to look like. And remember last time I said, if you're going to scale an axis, make sure you give me some indication. You don't have to label the whole thing. Just label the first tick mark, and that's good enough. If you don't label an axis, I assume you're going by ones. All right. So I try to keep that as straightforward as possible. You could also have what's known as a jump discontinuity. That's when you have a break in the graph and the break is in a vertical sense. All right, so there's a vertical displacement between different ends of the break in the graph. All right, so look for vertical displacement. In the break. All right. Now these are relatively, I'll say, reasonable values in terms of the pieces that make up the piecewise function. They're not absurd. All right. So we can graph this fairly quickly, I think. So we have y equals x minus 1. Y equals x plus 3. But the y equals x minus 1 only applies when x is less than 0. So I can plot my y-intercept of -1, but plot it with an open circle because y-intercept means that the x value is 0, and we can't quite get to 0. All right, so open circle there, and then count off your slope. Your slope is 1, so normally I'd say up 1, right 1, but I can't go to the right, so go left 1, down 1, or down 1, left 1, depending. So in this case, it's the same. All right, the next piece has a y-intercept of 3, also a slope of 1, so now up 1, over 1 to the right. And what we're looking at here is a discontinuity because there's a break in the graph, but the break shows a vertical displacement. All right. So when I say vertical displacement,
It's on the same x value.
generally on the same x value, yeah. If there's,
It
it doesn't have to be. We call those if there's a break that's both vertical and horizontal. So displaced vertically and horizontally, we tend to call that a gap. All right, but in terms of the vocabulary, it's not that big of a deal in this course. And you have your infinite discontinuity, right? So yeah, that's really all there is to a jump. You create the graph. If there's a vertical displacement, then you're looking at a jump. All right, infinite discontinuity. There's going to be the presence of a vertical asymptote. All right, when you have a vertical asymptote, one part or both parts will go to infinity vertically. All right, so we can graph this one fairly easily, I would say. Whether you use a calculator for support or if you just do it all straight by hand, either way is fine. Whenever I graph a rational function, I tend to do it by hand because I think we talked about this last time where, oh yeah, it was that very first example we did. You know, like the calculator sometimes gets a little kooky when it comes to plotting discontinuity. So I look for things like the x-intercept, y-intercept, vertical asymptote, horizontal asymptote, and or oblique asymptote. And most of the time it's just a sight recognition, right? Because if I'm looking for a vertical asymptote, I'm looking for x-intercept, I'm setting my function equal to 0. If I set my function equal to 0, cross multiply, simplify, I'm going to get x equals 0, right? So my x-intercept is at x equals 0. My y-intercept, if I have an x-intercept that goes through the origin, which is what's happening here, I'm going to have a y-intercept that also goes through the origin because the origin is both an x-intercept and a y-intercept, right? But if you're not sure, just replace every x value with a 0 and simplify. Even the most complicated rational function cleans up very nicely when you zero out all your variables, all right? So for here, for the x-intercept, you just set that top equal to 0. For the y-intercept, just find f of 0, meaning replace your function, in your function, every x, replace it with a 0. And you get f of 0 equals 0. Since y is equal to f of x, we would conclude that y is equal to 0. For the vertical asymptote, set your denominator equal to 0, but only if there's no common factor between the top and bottom. So it's kind of annoying, but the very first thing you should look for in a rational function is the presence of a point discontinuity. See if there's a common factor top and bottom, all right? And if, when you set that common factor equal to 0, if you get a solution, that means that you're looking at a hole. If you don't get a solution, then there's no hole in the graph. It is possible to have a common factor top and bottom and still not have a hole, all right? So that's something that, I'll show you an example of that in a second, all right? But in this case, we're just looking at vertical asymptote, x plus 1 is equal to 0, which means my vertical asymptote is x equals -1. Horizontal asymptote, we look at the relationship between the powers, right? If the powers are the same, then we're going to find the ratio of the leading coefficients. Question?
Wait, so the ratio of the leading coefficients means, like,
Oop, that's a little thick.
so like,
Those.
I know it's 0, right?
It's going to be y equals 1 in this case.
Plus 1?
Yeah, and that's because the degree of the top and the degree of the bottom are the same.
Okay, yeah, so it's just 1 divided by 1.
1 divided by 1.
That's right.
1 divided by 1 is 1. All right. Now, oftentimes you could pick out your not just vertical but horizontal asymptotes by looking at the picture. Sometimes it's obvious, right? Take advantage of those instances. And remember, if there is a horizontal asymptote, there will not be an oblique asymptote. So I'll just put a little no solution there. All right. So in graphing this, I'm going to plot my x/y intercept, which is at the origin. I have a vertical asymptote. I'll use a dashed line here. I'm going to make this dash, but the only way I can do it is to draw it and then erase parts of it. So just kind of bear with me on that. I have a horizontal asymptote at the line y equals 1. Same deal. Again, making it dashed. All right. Now I just need to know where the graph is going to live, all right? Because it's got to approach this line and this line, or this line and this, well, line segments, I guess, all right? It can't approach both. So if I can't have something like this, all right, because then it's not a function, right? So it's got to be one or the other when we're sketching graphs. And that's something else, I didn't mention this last time, but very, very often from here on out, all the way through the end of your studies in calculus, most often you're going to only be expected to draw a rough sketch of the graph, all right? Not point by point, not this picture perfect graph. Often, I'll tell you right now, there will be instances where that's all I'm going to need you to draw. Like if it's a polynomial function, I just need to know where the turning points are and things like that, right? So it's just a kind of a general sense of it, right? You could use your calculator for support here, right? The feedback I got over the years related to this course, specifically at this school, is that students liked taking all of their calculus here because we allow the calculator. Like if you're looking to transfer credits, like maybe you're just taking Calc 1 here, then you're going to transfer that to another school, and you'll take their Calc 2. They may be like, what calculator? Like, put that away. That's insane. That's not math, like that's calculator science, right? So just be mindful, and I'm showing you calculator techniques, but you should also consider the more analytical by hand stuff. All right. So what I use, and let me rewrite it because it's a little ugly. My handwriting doesn't make it much better. I use just a couple of test points, right? Because basically I'm just trying to determine if my curve is going to be above or below the line y equals 1. All right. Now, you could also sort of reason it out. And I'll show you the picture in a minute, but you sort of reason it out where I have an x-intercept here. The only way that I could have an x-intercept is if it went like this, roughly. It's not going to look beautiful. But the fact that I don't have an x-intercept over here means that my curve should be upstairs.
Are we going to be expected to write the other side, at least to put one point on the other side? Because
Like an actual plotting a point?
yeah,
Not, no.
I plotted like -2, 2.
That's nice. You can do that if you find it to be helpful. As long as you can determine where that curve lives, you're fine.
Okay.
All right. So yeah, if I wanted to do test points here, I might do something like f of -2, f of +2, and just see what I get. A -2.
+2 would be. No,
That would be 2/3, and that's still consistent with the curve itself. All right. So you do it that way. Like I said, and it's not unusual for, like I said, people to take all their calculus here, get up to differential equations, and then go to transfer to a 4-year. All right. So this may never be something that's unavailable to you. All right, so, but you know better than I do.
I think we actually.
I remember NYU was like, don't even think about it. We couldn't even use calculators for combinatorics.
That's unfair.
Learned the stuff though, I'll tell you that.
Oh,
Yeah, question.
What did you do with the x-intercept again?
X-intercept, you just set the top equal to 0.
Oh, just the top?
Yeah, well, you're really setting the entire function equal to 0,
Okay.
but in doing so, the denominator is going to cancel away.
Okay, yeah.
It doesn't matter.
is anything
Doesn't
divided by?
matter.
Yeah.
Divided by eight,
All right, so definitely a more analytic approach, but it's not anything too crazy. Right? I mean, there are some serious functions out there, like more Calc 2 when you investigate this, but
Remember last year I had a graph, like a sketch of two quadratic equations on each side of a rational equation.
those are fun.
Oh yeah, and without a calculator.
Yeah, without a yeah. So I just put a little trig expression in here, but it's a sine over sine plus 1. Like we'll learn how to take care of that kind of stuff. It's trig identities, but we'll get there. But yeah, to come up with this by hand, I
Isn't
mean,
that kind of looks like cosecant.
it would be if the numerator and denominators were flipped. If you could split it, then you'd have sine over sine plus 1 over sine, so 1 plus cosecant.
Is it the inverse and the
Reciprocal trig functions, yeah.
reciprocal of cos?
All right, so oscillating discontinuities, this is what I was mentioned before. I have the sine of 1 over x. Let me just bring this back real quick. Just make sure your calculator's in radian mode.
We no, because it would look nothing like it. It just kind of like there's like a straight line. And it's not.
Yeah, and the whole thing is that when and we're going to do this fairly often, we're going to graph ordinary non-transcendental functions on the same graph grid as a trig function, and if the units are not linear measures, so a radian is a linear measure, right? Horizontal distance, vertical distances, those are linear measures, right? You can't easily map a non-transcendental function on the same grid as a trig function if it's in degree form, right? You'd have to do a transformation on that, which can be fun, but more trouble than it's worth sometimes. Zoom trig. So zoom 7 or scroll down to the 7 and hit enter. And that's what our graph looks like. And that, it looks very different on paper, but, it's a little smoother rendering. But if I do a zoom in, just kind of bring it in, the more you zoom in, the more wonkiness you see. Yeah. Now it just looks like a barcode. Right. And it's very, very difficult to tell that there is a discontinuity at that location. But you can sort of use, we'll call it common sense, because in the sine function we have a variable in the denominator. So the one value that would make it undefined would be x equals 0. Right? So there must be a discontinuity there, but the problem is the more you zoom in, the more that muddies the water. So all I can tell at this point is that the discontinuity is somewhere between -1 and 1. All right? Because that's the amplitude. All right? You're only going up as high as 1, as far down as -1. At 0, somewhere between -1 and 1, there's going to be a discontinuity. It's just we can't really get at what it is without working with more advanced techniques, right? But basically, this is saying that if you see something involving a trig function with the argument having a variable in the denominator or a radical being involved, there's going to be a discontinuity in there somewhere. It's just a matter of categorizing it, right? Increasing, decreasing, constant, and continuity. It's a weird title. The first one's very straightforward. In terms of the pre-printed graph, if you don't see a break in the graph, then the domain is all real numbers, or a set finite endpoint. Right here we got arrows. It's going to the left forever. It's going to the right forever. I don't see any breaks along the way. It's going up forever, not going down forever. We'll get to that in a minute. But the domain here, I would say, is -infinity to infinity. The range all possible values of y, right, doesn't go down forever. It stops here. It's just a little shot. The graph got a little screwy. You can see it's offset by a smidge. This is actually supposed to be 1, 2, 3, 4, 5. It's supposed to be at -6, so just kind of pretend there's a point there. All right, so we're going from -6 on the low end, bracket, because we can actually get to the -6. All right. Just remember, if there's curve there, that's like saying that there's a closed circle at that location. All right, it's just we don't really, I mean, it would be kind of crazy. We'd have to draw it like this if we were to do closed circles everywhere. All right, it's only an open circle if you see an obvious open circle. All right, so you'll see that, like I try to like make it really dramatic. Yeah, like open circle, it's right there. You can't miss it. If you don't see one of those, there's no open circle. Right? It does go up forever, so I give it a positive infinity on the high side. And remember, infinity always gets parentheses because it is not finite, so you can't capture something if it's always on the move. Or always one step ahead of you. Increasing, decreasing, constant. Increasing, when we talk about increasing, decreasing, we're always reading the graph from left to right. That'll change when we talk about limits, in which case we'll read it from both directions. And then when you get to Calc 3 and you get into three-dimensional spaces, and you'll get it from left, right, backwards, forwards, obliquely, in every possible direction. It's very circular.
For increasing, decreasing, how would you like write the answers for that? Like in what form? Just
Interval notation.
okay.
Yeah.
So parentheses.
parentheses or brackets where appropriate. So let me highlight the increasing components.
Yeah.
So that's going to be this part here. All right, so what I have in green is my increasing. Yeah, color code that. All right, we're talking about, so the intervals over which it's increasing would be from the lowest x value possible to the highest x value possible. All right, so this one is going from 1, 2, 3, 4,
-5
Yep.
to -2.
to -2. Yep,
So you would put those in brackets, right?
yep,
And then the infinity would have parentheses on it.
yep.
But the bracket for 1 would be.
Let him get to it.
No, I'm just trying to figure it out.
Let him get to it.
Yeah, so it's going to be from -5 to -2, x value for which the increasing interval starts, x value for which the increasing interval stops. Then it starts up again at 1, and it goes on to positive infinity. All right, so we're thinking in terms of x values when dealing with increasing, decreasing, constant. All right, we will connect these two with a union. All right, so we're basically uniting those two intervals to make up the complete interval for which the function is increasing. For decreasing, same idea. You're just going downhill from left to right. Now, just be careful. People get confused by this. You see an arrow, and that arrow makes it really feel like you're going uphill. It's not really so much about where the road is going. It's where you're going on the road. All right. So you're traveling along this pathway from left to right. Even though the pathway extends to negative infinity, that doesn't mean that's the way you're walking, right? So here I'd be skiing downhill, whereas with the green I'd be basically taking my chairlift up to the top of the mountain. All right. So these two intervals, right? The first one starts at negative infinity, and it stops decreasing when it gets to that turning point. That turning point is the end point for which the function is decreasing and the beginning point for which it'll increase. All right. So it'll go from negative infinity to -5. Then it'll pick up at -2 and go to 1. All right. Now that has finite endpoints, so that gets square brackets on it with a union. All right. When you write the interval notation representing anything, domain, range, increasing, decreasing, whatever, make sure that any relevant pieces are connected with a union. All right. Constant, irrelevant in this case, and that's because it never flatlines. All right. So we don't have any instances in which the function is constant, and we don't have any instances in which there's a discontinuity because there's no break in the graph. All right. So constant would be an interval for which there is zero slope. You just think of it this way: increasing, positive slope; decreasing, negative slope. The only other possibility is that the slope is 0. All right. That would be the instance in which the function is constant.
Okay. So like if it asks for an interval where it's constant and there's only points, then no. If it asks for points, then we just write down.
Well, you're gonna do the same thing. You're gonna indicate where that interval starts and where it stops. We'll see that in the next example. All right. So in the next one, it doesn't extend to negative infinity, and again, it got offset, and it's really aggravating. This point here should be at this location. Everything else, I think we can kind of make work. So that's 1, 2, 3, 4, 5, -5. So the domain of the function starts at -5. It continues on until we get to that open circle. That open circle is at 1. So we're going to go up to 1, but we're going to put a parenthesis around it to indicate that that's the target value, but we're never actually going to get there. All right. Then that second piece starts at 1, and there's no break. Even though it comes to a kind of a corner there, there's no break in the graph, so it is continuous going from 1 the rest of the way to infinity. All right. So that arrow, in terms of x, would eventually get out to a positive infinity. I was going to write a positive symbol, but infinity gets the job done too. All right. Now for the range, lowest possible value all the way to highest possible value, there could be breaks in the range just like there's breaks in the domain. In this case, there isn't, even though it looks like there is. Every y value is accounted for between 1 and 5. And you may look at it and say, well, wait a minute, I got a open circle there at 4. But I also have a line here that covers the y value of 4. All right, so if you think about it, like I'm going from 1 all the way up to 5, is there ever a moment where I skip over a y value? At first glance, you look at the open circle and say, well, that's one of, oh wait, it's covered by all the other points, the infinitely many points that are along that ray. All right. Increasing, decreasing, same deal as before. Sometimes a little easier to see when you're dealing with linear expressions. So you got increasing there, downhill, so decreasing there, constant here. All right. I try to color code wherever possible. Sometimes it's not really necessary, but sometimes it can be helpful. And I know you're generally not color coding on your own papers, but this is all saved in PDF form, so when you're reviewing, you're like, oh, how did you know that that was increasing? Oh, look, the green, that's the going up, and that makes sense. All right. So increasing is happening on the interval of 1 to 3. The endpoints exist on that interval, so we put square brackets on it. For the decreasing component, that happens over the interval of -5 to 1. There is a finite point at -5. I think I said 5 to 1. I meant -5 to 1. There's an open circle at 1, which means that there is no point there along this pathway. So I would put parenthesis on that one, all right, to say that my decreasing component of the function it will in fact decrease up until the infinitesimal moment prior to getting to the x value of 1. Then for constant, flat line starts at 3. There's a finite point there, goes on to infinity, parenthesis, because infinity is the definition of not finite. All right. And then any points of discontinuity. Now this is something that, it could go either way in terms of how you represent it, but the standard practice is to indicate only the x values for which a function is not continuous. All right. So the only x value for which this function is not continuous is x equals 1. All right. So at the x value of 1, there's a break in the graph. It's only at that particular x value that there's a break in the graph, right? I'll have people say like it's 1, 1, 1, 4. Like they're given coordinates for the breaking points, and it's like, well, that's not telling me what I want to know, right? So when I say any points of discontinuity, and it's weird because points oftentimes means coordinates. So you would think that maybe you want the 1, 1 and the 1, 4, but we just want the x value for which the function is discontinuous. X value or x values. All right, so limits. We'll focus on instances, initially at least, where the point of interest, the limiting constant, we call it, is approaching or leads to a graph that's approaching some sort of asymptote, right? So I'll give you some rules, I guess. I'll call them rules. So start off with the structure of a limit. All All right, so we have limit as x approaches c for some function of x, the result of which is L. All right, so this is what we call the limiting constant. This is my function, which you probably don't need to label because that should be obvious at this point. And this is actually the limit. All right, so the result L is the limit. All right. The only way a limit will exist is if the limit coming in from the left-hand side is the same as the limit coming in from the right-hand side, right? And that particular value actually exists. It's a real number, right? So I'll say rule limit as x approaches some constant c from the left. All right, so make a little note of that. This is approaches c from the left of f of x if that's equal to the limit as x approaches c from the right, applying to the same function, right? And just bear in mind, a piecewise function may appear to be two separate functions, but a piecewise function is all part of the same function, right? So it's still most likely f of x, right? And so this is dot, dot, dot from the right. That will be equivalent to the limit as x approaches c overall for the function. And it'll only exist if those values are the same and themselves exist. Over the years, I've had kind of a back and forth on, like how much time do I spend with limits, because I know people want to kind of get to the more interesting stuff. But then when I shortchange the limit conversation, what ends up happening is when you get to the more advanced levels, or even just later topics in this course, but more so the more advanced levels, there's a deficiency in individual students' knowledge of limits, right? And so the idea that, yes, you could find a derivative, but sometimes we need to find a limit of a derivative, right? And so you'd have to have all your limiting skills, but then also the derivative skills, and then and really you kind of go down a rabbit hole here by saying, like, well, the basis of a derivative is a limit. So then a limit on top of a limit, what does that mean? So all this stuff really becomes critical to your like deep understanding of calculus.
So like the last one on the right, like limit f of x x to c, is if both the left and right are the same limit?
Yep.
So like if c is the same number, or sorry.
Well, C would be the same. It's just a question of whether you're coming in from the left or the right. But the resulting limit L
Yeah.
would only exist if it's the same for both sides.
Okay, got it.
All right,
Thank you.
no problem. Now, for a question like this, you see that involves creating a graph. There are ways to handle it without actually doing that. But if I were to replace the x value in the function, so if we're not doing this analytically, but just kind of steal my own thunder a little bit. When you find a limit analytically, generally it's just substituting whatever the limiting constant is into the function. Doesn't always work, but it's a good kind of a practical approach. Not even practical. It's just like a rule of thumb. Like you just kind of assume that that's going to work. Sometimes it doesn't, but most of the time it will. Right? But in a case like this, if I dump the 2 in for x, I'm going to get something that's undefined. If through direct substitution you get a limit that's undefined, that could mean that the limit does not exist, but it could also mean that the limit exists, you just haven't figured out what it was, right? So oftentimes you're going to go to a graphical approach, or at least consider what the graph might look like. And that's what I was talking about before when I was saying you probably don't want to have a point-by-point graph. Sometimes you just want this and to get an idea of what's going on in the picture, right? But let me graph 1 over x minus 2, all right? So there are no x-intercepts, because if I take the numerator instead of equal to 0, I get 1 equals 0. It's a contradiction. Vertical asymptote, x equals 2. All right, so I'm going to draw a dashed line here. A vertical asymptote is just a boundary. So, I mean, you could label it with arrows if you want. I know when I taught pre-calc, I kind of harped on like proper labeling, just because they're sort of getting their feet wet with this sort of thing, and even algebra, college algebra, algebra 2 in the high school. But really, you don't need to have arrows on it. It's a boundary. You just need to have a sense of it. My horizontal asymptote is going to be the line y equals 0, and that's because the power on the top is less than the power on the bottom. And when I say power, I mean the highest power. So whatever the degree of the numerator is and how it relates to the degree of the denominator will dictate whether or not there's a horizontal asymptote. If the power on the top is less than the power on the bottom, it's going to be a horizontal asymptote of y equals 0. If it's the other way around, then there's none. If they're the same, then it's the ratio of the leading coefficients. Now you may look at it and say, well, the power here is 1, the power here is 1. That's not true. That 1 has an understood x to the 0th associated with it. So the power on the top is, when I'm talking about that, I'm talking about the power of x. There's only a constant, x has a power of 0. So the horizontal asymptote is just going to be y equals 0. It just defaults to that. All right. Then in terms of the curve itself, you could use some test values. You dump a 0 in there. That's a nice, easy number to work with. You know that you're going to get a negative, which means you're below the axis. Specifically at negative 1/2, if you want to be a little bit more precise, that's fine. We just need a general shape of the curve. All right, if I dump a 3 in there, I get a 1. That'll put me right there. There are no common factors top and bottom. No common factors top and bottom means there is no hole in the graph. All right, so I don't have to worry about an open circle anywhere. All right, so the first question here is asking me to find the limit as x approaches 2 from the left-hand side. All right, so what I do, it's very juvenile, I think, but I draw like a little dude, because like I was saying before, I just kind of look at it like the graph is the path. It's how you walk along the path that determines whether it's increasing, decreasing, constant, or what the limit is going to be. So I have a little dude standing on the left-hand side of the graph because I'm coming in from the left. That dude is traveling along the path. We're at an x value of -2, -1, 0. I'm at 1. I'm at 1.5, 1 3/4, 1.9, 1.99999. As I get closer and closer to the x value of 2, it seems I'm going downhill, right? So I'm going downhill where? Well, there's an arrow. I'm never going to stop going downhill, right? So that means I'm going to a y value of -infinity, right? So from the left-hand side, as I get closer and closer to the x value of +2, right? That negative sign after the 2 means you're coming in from the left. I'm getting closer and closer to -infinity. All right. And if you're really unsure about it, again, you have a calculator. You can do that. It's a little kookier when it comes to the graphing calculator for limits that go to infinity, but it is still somewhat. You know what? I'm going to put it in as a fraction, not a fraction, a division instead of a fraction. Let me just do this real quick. 1 divided, because I want to actually see the decimals. X minus 2. All right, so I go to my table. You can look at the picture, but we already have the picture. I'm confident, so we're going to leave it there. But as I get closer and closer to 2, the x value of 2, so I'm going down the line here. Let's say I'm starting at -6. You could see that the y value is becoming more and more negative. And you'd say, well, what do you mean it's going to negative infinity? It seems like it's at -1. All right? But what I could do, and I will preface what I'm about to show you by saying, not everybody likes this technique, so feel free to not like it. You're not going to offend anyone. All right? You go into the table set,
You can lower the table,
delta table, make it tiny.
like 0.00001.
That works. All right? Just make sure your table start is at whatever your limiting constant is. All right? So limiting constant goes in for table start. This is second window, by the way, if you missed that. Second window. Table start is whatever your limiting constant is, and then make your delta table very tiny. Go into the table again, center it around, and you could see
Definitely goes towards.
it's going to something extremely negative. All right? So that's a pretty good indicator that negative infinity is an appropriate conclusion. But you can make the delta table even smaller. Eventually, you could go too small, and then it'll throw an error. But for now, you get the idea. It's getting fairly extreme. All right. So you could do that, or you could visualize the graph, and you don't have to draw a little dude, but you do it for instructional purposes. If you're coming in from the right, it's the same idea, except you're going up forever. All right, so that's going to get you to a positive infinity. Now, the part C here, and questions are not always going to be itemized like this, where I'm going to say, coming in from the left, coming in from the right, what's your conclusion? Right? Sometimes it'll just say, what is the limit as x approaches whatever, and you have to know to do those things behind the scenes. Right? If the limit coming in from the left is not the same as the limit coming in from the right, then the limit does not exist. So we just say d and e. All right? And that's because, well, again, negative infinity is not equal to positive infinity. All right? And there is some gray area as it applies to whether infinity can be equal to infinity. Right? There's a philosophical. I don't even know why I said it that way. Philosophical interpretation, and then there's a practical interpretation. So the idea is that they're both going to the same neck of the woods, all right? But there is a school of thought that infinities could never be equal to one another, right? Because there are different types of infinities. That's a different conversation for a different day. All right. The next one, same idea. All right, so we label up the graph. We have an x-intercept of 0, so you can plot that. A y-intercept, also 0, but you kind of know that if the x-intercept is at the origin, that must also be a y-intercept. Right? Maybe there's an additional x-intercept, but there could never be an additional y-intercept. Wouldn't be a function. It would fail the vertical line test. All right? I'll get my vertical asymptote, which would be at -3. I'm going to, again, dash it up. Oops, over-dashed it. My horizontal asymptote, because the powers are the same, my horizontal asymptote is going to be the line y equals 1. Again, for horizontal asymptote, if the powers are the same, we find the ratio of the leading coefficients. All right. So y equals 1. Again, dash it up. All right, so I'm going to draw my curve. I could use test points. I could cheat and use the calculator. I know that one of them has to be down here. Poor quality curve, but because there's an x-intercept there, so it has to go through that point, and that point is below the horizontal asymptote. So
I'm still lost on how we find the x and y
intercepts.
intercepts.
Oh, yeah. So the only reason we could do it very fast is because this is a simple enough function that it allows for that to happen. You're setting the top equal as 0 for the x-intercept.
Okay.
So x equals 0.
So then I'm just at 0.
Yep. And
Y
because,
is 0 as well in this particular.
say it again?
And then the y-intercept is
Y-intercept is 0 also. If the x-intercept is at the origin, the y-intercept must also be at the origin.
Right. And
If-
what would be the result to find the y-intercept quickly?
Swap out any x for a 0.
Right. Yeah.
All right. So then a negative, as a test point, I could throw a -3 in there. Well, actually, no, -3 would be ridiculous because that's where the vertical asymptote is. -4 over -1 would be +4, so we're in the positive neck of the woods. So we're looking at something like this. All right. Again, I mean, I'm allowing the calculator, so use it. Just kind of know where you're going. Like if you're like, well, this is the last math class I have to take before I transfer to another school, at which point I'm going to pursue a career in theoretical mathematics, you better know how to do some of this stuff on paper and in your head, right? But if you're going to do the full slate of calculus, differential equations, everything here, and then transfer away, then you could rely heavily on the calculator and be just fine. Right? Let me grab my little dude here, which probably never thought you'd hear in a math class. So anyway, coming in from the left, looks like I'm going up forever. Coming in from the right, looks like I'm going down forever. So it's the same deal. Up forever, positive infinity. Down forever, negative infinity. If they do not agree, it's a DNE. All right, these two, coming in from the left, coming in from the right, need to be the same in order for the limit to exist. All right. And, have to be finite. So obviously they're not all going to be the same. Like it's not all going to be DNE. There will be instances where we can get an answer. All right, so bring us to the next one. For this one, because again, I don't kind of feel like I'm beating a dead horse here with the doing it by hand. Let me show you the graph of the next one, just so we can kind of cut some of the fluff here. We'll do a quick sketch of the graph based off what we see in the calculator. You could determine immediately that there are two instances for which this function would be undefined. That would be when x is 2 and x is -2. But you could also pull that from the table because the numbers are fairly nice. All right. So the thing is, because I changed my table setting, right? I changed it to have a start value of 2. I think it was 2. And the delta table was tiny. When I go into the table now, I have all these funky decimal values that I probably don't want. Actually, it kind of works out nicely over here. But maybe I don't want that. If that's the case, you go into second window and change these back. The default settings are 0 and 1. All right, so 0 and 1 for the table start and the delta table. All right, so take a look at the picture. We'll do a zoom 6. You see that there's a vertical asymptote at this location over here, which appears to be -2. All right, so we're going to rely on that. I'll draw my vertical asymptote. I know that this curve is going downhill. In the picture, even though in the table I see that there's an error at +2, I do not see a vertical asymptote at +2. That's going to be a discontinuity. All right. So there's going to be a hole at x equals 2. The table is pretty much telling us where that hole is in terms of the y value. Because right before we get to 2, we're at about 0.25. After we get to 2, we're at about 0.25. It's logical to assume that the location of the hole is 2 comma 0.25. So open circle there. I'll make that a little bit more obvious. Draw the curve coming in and out of that. Based off the diagram in the calculator, the graph, it does appear that we have a horizontal asymptote. It,
Y equals 0.
it looks like y equals 0. It doesn't look like, when it comes in from the bottom, it doesn't look like it's ever going above it. When it comes in from the top, it never looks like it's touching it or going below it. And you could actually trace that out using the table in a sec.
I did like the M was less than N.
Yep.
Because, yeah. And then I just knew it was 0.
Yep.
That's right.
That's correct. All right. Now, if you forget your rules for horizontal asymptotes, you're in the middle of a test and you're freaking out, I don't remember the rules, one thing that you could do is go into your table setting, make your table start, it really doesn't matter, just make it, I'll start with 0, and then make your delta table something large. All right, so let's make that, instead of 0.0001, let's make it 1000. So 1,000 for the layperson. All right, so go into the table. As I increase towards positive infinity, it looks like my y value is getting smaller and smaller, but never going negative and never hitting 0. So it appears as though it's approaching 0. Right? If your y value, so essentially your limit as x approaches infinity, if it's getting closer and closer to 0 and not actually touching it, that would be the limit. The limit would be 0. Right? And that's one way that you could identify. I mentioned that last time, talked about the horizontal asymptote rules, and I said, if there's another way to find horizontal asymptotes, and it involves us knowing about limits. Now that we have an idea about limits, if I say that instead of x approaching 2 or negative 2 or whatever, it's approaching a positive infinity, so it's getting larger and larger and larger, what's happening with y? Well, it seems to be getting closer and closer to 0. It's a pretty good indication that you have a horizontal asymptote at y equals 0. All right, but again, you might find yourself getting frustrated. I'm all the way out here at 232,000. Go back into the table set, default it to 0, 1. All right, now as it applies to limits, just make sure that your independent and dependent is set to auto. When it comes to finding like particular y's, when you know an x, if you want to find a y, if you know a y and you want to find an x, then you could put it on ask. But for limits, for this topic of limits, you're better off having it at auto. All right. So right back to square one. Now we can actually answer all the questions that are being asked. So the first one is, as I approach a positive 2 from the left. All right. So little dude here. When I find limits, there's different ways to think about it. I really only focus on the part of the curve that immediately surrounds the point of interest. So I could start over here, in which case I would say, I'm going to the right, because I'm starting on the left, I'm going to the right. I get down to negative infinity, I'm magically transported to positive infinity, and I continue on. Or I could just say, well, I'm starting here. All right? This is the relevant part of the curve, so let me just start here. As I get closer and closer to the x value of 2, the y value I'm getting closer and closer to is the y value of this hole. Right? The coordinates of this hole are 2 comma 1/4 or 0.25. So the y value I'm getting closer and closer to as I move in from the left towards the x value of 2, the y value I'm getting closer and closer to is 1/4. Coming in from the right, same deal. I'm starting at a value that's very, very close to 0, but as I move in from the right, going left, I'm increasing ever so slightly in terms of y until I get to that location, which has a y value still of 1/4. And like I said before, If the limit from the left equals the limit from the right, and it's finite, that is your limit.
So in the past, it didn't exist because it wasn't finite.
Correct. And they were also going to different infinities.
It wasn't approaching the same.
Right. Couple more. Then they go fairly quickly, so I'm not going to keep you too much longer. So f of x equals 1 over x squared. No x-intercept. Right? Vertical asymptote at the y-axis. Right? And that's again because there's no common factor top and bottom. So I don't have to worry about there being a hole. And I glossed over that in the last problem because we did it very much calculator style. But there, if you did factor that, you would see that there's a common factor top and bottom. It happened to be x minus 2. So you could have done it analytically. But here, not even remotely an issue.
Is it just both, like x and y axis? Yeah.
Yep. Now this one you can kind of reason out the graph because we know what a rational function curve is supposed to look like. It's one of these, something like that, right? For this particular function, there's no way it could ever be negative, right? 1 is a positive number, and on the bottom you're squaring whatever you get. Whenever you square a number, it becomes positive. So it's positive over a positive in all cases. So it must be a curve that looks like this. It's actually supposed to be perfectly symmetrical, but because I was gifted a passing grade in studio art in 9th grade, you get what I'm capable of, which is not much. Artistically, that is. All right. So we're approaching 0, and one thing you got to be mindful of, and it's very important, just because there's an asymptote at 0 doesn't mean that's what the question is asking you about. In this case, it happens to be. But remember, in the last case, we had an asymptote at x equals negative 2. But the question was asking about x equals positive 2. All right? If I said, what's the limit as x, for number 3, if I said, what's the limit as x approaches 0, I'd be talking about this location over here. In which case, I would just report whatever the y value is at that location. Because if it's continuous, and that's something to keep in mind, if you're looking at a continuous function, no breaks in the graph, then your limit at any particular value of x is just going to be whatever the y value is at that location. All right, so you'll see that as we go forward, but just because a question has or a graph has a discontinuity does not mean that's what the question's asking about. All right, in this case, it happens to be that way. So as I come in from the left, let me get the little dude here. Coming in from the left, as I get closer and closer to the x value of 0, it looks like I'm going up forever, so follow that path. Coming in from the right, same deal, going up forever. Because this is a symmetric graph, they will actually be going to the same infinity.
Yeah.
So my limit will be infinity. All right? But if it was not symmetric, they could be going to different infinities, but we could still say that it's going to some kind of positive infinity. But it's not very mathematically sound to write some kind of positive infinity. So we just abbreviate that with just another infinity. But then you have the whole, like, I'll call it philosophical for a lack of a better term. But because people, they kind of reason it out. They say, well, if it's going to infinity, then that means that it's limitless. Doesn't that mean the limit does not exist? Well, no, the limit exists, but it's infinite. All right? So you kind of get into that. Yeah, the limit the limit would be at infinity if you could ever get there, right? So, but what a lot of people say was the limit does not exist because there is no limit. Isn't infinity the fact that there is no limit to something? We gotta move away from the idea that a limit is like the speed limit. You know, like it's not a maximum. Maximum is the maximum, right? The limit is more of a destination, right? You may be able to get there, you may not be able to get there, but if you're targeting the same destination, that would be the limit, right? So, I mean, I could be driving to Buffalo tonight, and so could you. I'm starting here, you might be starting in Toronto. We're both aiming for the same location, so our limit is Buffalo, right? That's more along the lines of it, right? So it's kind of weird because the more you think about a word, the more it could be confusing. But
If I said does not exist, do I get points off?
yeah, because when we say a limit does not exist, we're saying that there's some sort of contradiction from the left side to the right side, right? So a limit not existing would be the fact that if I follow the left path or the right path, I'm going to two different locations. I call it the case of the missed high five, right? So limit does not exist. Does exist, depends on where you're going, but you know, that's really the long and short of it. This graph obviously is a little crazier. If you look at the factors of the bottom, now I'm actually gonna find the factors of the bottom here because I want the vertical asymptotes, right? If they exist, and if there's a hole, I want to pull that out too.
Oh, it's gonna be vertical asymptotes. I just factored everything.
Yeah.
X minus 3. Sorry, it's x plus 3 and x minus 5.
Yeah.
And then the actual things are x equals negative 3 and x equals positive 5.
Yeah. And we also have horizontal asymptote,
Yeah.
and that would be
My mind's blanking.
power on the top is less than the power on the bottom,
Right. 0.
so 0. We have an x-intercept. Set the top equal to 0, x equals 1. The y-intercept you get by slotting in a 0 everywhere you see an x. So it's kind of like just cover up anything that has an x in it and simplify the rest. So all of this would be gone. You're left with negative 1 over negative 15, which is just 1/15. Not the easiest thing in the world to plot, but you can kind of ballpark it. Then we just need the shape of the curve. So let me get those asymptotes in there. Negative 3. 1, 2, 3, 4. I'll dash it up in a second. Horizontal asymptote, maybe not the most visible thing in the world. Get my x-intercept at 1. X-intercept at 1, yeah. Y-intercept at 1/15, and like a smidge here. Okay. Now, this is kind of weird because you wouldn't think that you would necessarily be able to cross an asymptote. When you're dealing with horizontal asymptotes, they only really become relevant for extreme values of x. So if you're centrally located, you can cross this horizontal asymptote many, many times. Happens with trig functions a lot. But once you start getting out towards the extremes, that's when it needs to settle in on whatever y value it's approaching. All right? So here I have a point above the x-axis. I can throw in a value if I want, but it looks like the trend has it going something like this. So we're going here. Well, that's weird. So it could turn around and go back up, or it could continue down this way. So really I just need, okay. So I could just pop in to verify that. I could pop in a larger number like 2. So we'd have 2 minus 1 is 1. Then plug in the 2 on the bottom, 4 minus 4. So negative 15. No, negative 15 on the bottom. So this is going to be negative 1/15. So that's going below. So it does have a little bit of symmetry in that regard, but since it's going below, it's reasonable to assume that it's going to continue going down.
Kind of looks like you split, like one of the simpler ones with like an x to the third.
Right, yeah, it's got a little cubic feel to it. Absolutely. All right, and so then we could test a value that's a little bit less, so like f of negative 4, f of 1, 2, 3, 4, f of 6. Get those values. You could also, like I said, you could dump it into a calculator and go from there. All right. But because we have no intercepts in this region or this region, then we know it's going to be cordoned off by those two asymptotes. So we put in a negative 4, I get a negative 5 up top, 16 plus 8 minus 15. So it's negative 5, so it's negative. That's all I really care about, the fact that it's negative. So we're looking at something like this. And then plug in a 6, you get a 5, 36 minus 12 minus 15. It looks like it's going to stay positive. Yeah. So we're looking at something like this. All right, again, the idea is that we get a sense of the shape of the graph. You can plug in and simplify as much as you want, but once you get the idea, if it's a choice between positive and negative, once you know that it's going to stay positive or go negative, then you got what you need, so you might as well just move on. All right. So now, the way this question is structured, we have x approaching 5, x approaching 0, x approaching negative 3. It's not like the previous ones where you have approaching 2 from the left, 2 from the right, and then 2 overall. These are 3 separate questions. You have to know that behind the scenes, we're looking for the limit as x approaches 5 from the left of that function, and the limit, so I'll put a little question mark because we don't really know yet, the limit as x approaches 5 from the right of that function. All right. If they're the same, that's my limit. If they're not, then the limit does not exist. All right. It just so happens that for the first one, we're approaching that asymptote, the one on the right. The left side of that asymptote's going down, right side's going up, missed high 5, limit does not exist. 0 has a finite value. There's a coordinate at 0, 0 comma 1/15. We're interested in what's happening to y as they come in from the left and from the right. We're approaching the same location, this coordinate, which is 1/15. Well, not the coordinate, but the y value of the coordinate. And then at negative 3, that other asymptote coming in from the left, we're going down. Coming in from the right, we're going up. Missed high 5. Limit does not exist.